Hey everyone, I'm Dimi, and I'm the smart contract developer for Pyreplay. And yeah, this talk is about Merkle Trees and how you can use them as a means of authorization for things like, for example, NFT whitelists or payment pools, which we would like to use in Pyreplay, maybe. So the thing is, the presentation was actually done for Ethereum first, so I don't really know how well, like fee-wise, how much you would save on Alph. But I heard, for example, since you have maps on Alph and you always have to log 0.1 Alph inside a subcontract, I guess at least you wouldn't have to spend this money in the beginning. So yeah, let's look at the motivation. So yeah, Fugasho and I had an NFT project, and for this we needed a whitelist. And the thing is, storing data inside a smart contract is quite expensive. And like to push, for example, 1,000 addresses into a contract would have been around $600 back then, which is completely insane. And on the other hand, computation is less expensive. And yeah, with Merkle Trees, you can basically submit a constant piece of data, and you can just yeah, then basically inject a proof when you call a specific function, and yeah, can still authenticate people. And yeah, that would have been basically just $5 around that time. So yeah, the Merkle tree was invented by Ralph Merkle as part of his digital signature scheme. And Merkle trees are actually used in a lot of applications. Like, for example, you obviously use Git, I hope. There it's part of the object database and enables features like deduplication and conflict detection. Then it's, for example, used in the IPFS, where you would check for data integrity. So normally you receive parts of data, and then you can verify that the data wasn't tampered with. And yeah, so in general, I'd say there are two things you can do with Merkle trees. First, you can yeah, verify the integrity of the data, or verify the inclusion of some piece of data without having the full data set. Why not the full data set? You will see that soon. So let's look at some, like how a tree is built. So the basic data structure is a binary tree. And for example, here on the bottom, we have like transactions, and this is our data. What we do with that is we would hash each piece of data. So we end up with the hashes in the, you can see that right, in the lowest row. And from here, we would go up. So we concatenate always pairs of hashes, get another hash. And then we do the same for the next row, get another hash, until we end up at the root. And this is this piece of data which we would, for example, store inside the smart contract. So now we have created the Merkle tree. From here, to verify whether some piece of data is part of the tree, you can do the following. So for example, on the bottom, we want to test whether transaction 2 is part yeah, of our data set. So what we would need for this to end up at the root hash are hash 1, hash 34, and hash 5, 6, 7, 8. So basically, we would take the data, hash it, and then basically walk this flow only to the root hash. And in the end, if we end up at the correct root hash, then we know that this piece of data is really part of the tree. And yeah, as you can see, we don't need the full data set to end up at the root hash. And normally the proof size is the height of the tree -1, so it's way smaller. Yeah, so let's look at some use cases. I already said the NFT whitelists are a thing, for example. So if you have a large amount of users, like 1,000 to 10,000, you obviously prefer it to be cheap for the owner, so for whom you're creating the contract, for example. And yeah, and with the Merkle tree thing, you can basically split the cost among all the users, among all the minters, and then it's not one big piece of tokens you have to spend in the beginning. And I have prepared two solutions, which are yeah, basically a map and a Merkle tree to kind of compare them. So now it gets a little technical. Can you see that in the back? Okay, shit. Sorry. I could try to make it maybe a bit bigger, I guess. But then, yeah, it's not getting bigger. I mean, so the stuff here on the bottom is just the mint logic to create the NFT, so that's not the interesting part. Is that better? Yes. Okay. So map implementation. So we basically have the contract. It's really just a tutorial contract which is present in the docs. And we have our mint function. I removed everything else here. And yeah, the interesting part is the whitelist logic, how it would work here. So we have here a mapping from address to bool. So the address is this is basically the whitelist. So what you would do before you start the mint is you would push addresses into this mapping. This is the expensive part. And basically you would put them with false. That just means that the user hasn't yet minted the NFT. And the whitelist logic then would just take the minter address, would look into this mapping, check whether a minter is present inside there. If not, he's not whitelisted at all. And yeah, then additionally, we have to check whether the flag is true. If it's true, he has already minted, so we also reject him. And afterwards, we just set the flag, and this would basically allow him to mint and trigger all the mint logic at the bottom. Yeah. So then we have or maybe questions right now? Then we have the Merkle Tree implementation. So what changes here in the contract is, I said we have this constant piece of data which we have to provide to the contract. So this is what we now give to the contract when we create it. We give it the Merkle root. And I have here a subclass Merkle proof. It's from KR Coder. Is he here, by the way? No, he's not. Okay. So yeah, that basically holds the Merkle root and stores it, and has the logic to verify a proof. And what we now have additionally is that the mint function also takes the proof itself as an input parameter. So we have to, or the user has to inject the proof into the function. And yeah, the whitelist logic is in the end similar. We first look at this. So we have again this minted mapping, but this time we don't populate it. We just keep it to store the data that someone has minted an NFT. So to kind of track the state. So we can just check here if the minter is not inside the minted map, then he hasn't minted yet. And then we verify the proof. So the proof is just a vector of bytes, basically, of all those hashes we had. Plus, we also now hash the address of the minter to produce the leaf node. And yeah, we will verify this. If it's a valid proof, he is allowed to mint. So we track the state that he has minted, and then we trigger all the mint logic. Yeah. So architecture-wise, that changes some stuff. For example, normally you just have a front end plus the backend with which you interact. I have this here as contract. But we need the proof now. So we need an entity who provides us the proof, who has the full Merkle tree in theory. So the flow here would normally be, so the user or the front end talks to the backend, sends his address there, a proof is created, returned to the user, and then the minting flow is triggered with the contract. So the cool thing is you can merge the user and the backend in theory together and just place the whole Merkle tree inside the front end, because we can expose it, and since no one else besides us can change the Merkle root, it's still safe to just expose the whole tree. Yeah. So I have also an extension of the whitelist thing, and this is what we would like to use in Pyreplay maybe. So there it could be that we have games where a lot of people play at the same time, so we kind of have a pool of tokens and we have to distribute them across all the users. And yeah, okay, I'm not sure how fee-wise it would be if you just send 1,000 transactions out. Probably cheap. If not, then a payment pool would make, for example, sense. So how this works is that we now change the leaf payload. So before that, we had an address, and now we have a concatenation of an address plus the amount of tokens someone can withdraw from the contract. So yeah, again, we need at the top some state where we track how much tokens have been withdrawn so far. And so the withdraw function basically, again, has the proof, plus part of our payload in the Merkle tree is the maximum amount. And we also have here the amount the user wants to withdraw. Actually, yeah, this can be simplified because you could withdraw just everything. But yeah, you could also split this up. So the payment logic in the end would basically look at this withdrawn map and check how much tokens have been already withdrawn. So this is the base we start from. And then the checks are just, so we look at the amount the user wants to withdraw and how much he has withdrawn so far. And this basically has to be smaller than the amount we have in the Merkle tree. Yeah. And yeah, if it's bigger, then this exceeds the withdrawal limit. And yeah, the second check is basically to verify the proof. And yeah, this time we would put together the withdraw and the max amount as the leaf payload and would verify the proof. And in the end, yeah, just track the state of how much has been withdrawn, basically. So yeah, those are payment pools. I also have another example where Merkle trees are used. Shit, too early. Yeah, Merkle trees on Polygon. That's also quite cool and makes especially sense for them. So yeah, you have all this. So first of all, they have like 3 chains. They have Ethereum, they have Heimdall, cool name, the gatekeeper basically, and Bohr. And Heimdall is looking on Ethereum and on Bohr. And for example, in the deposit flow, Heimdall would inject the tokens which are to be bridged from Ethereum to Bohr, and would just put them on Bohr. And I think this is the cheap part because Polygon is cheap. And on the way back, the thing is, Heimdall can't do that because for each time if they want to update a balance for a user, they basically have to pay a lot of fees to do that. So what they are doing is basically aggregating a lot of withdraw transactions and then just publishing a Merkle proof. And users can then query the Merkle proof from Heimdall or from their API basically, and then put this as part of their payload to the contract. Yeah, and have an Angela Merkle tree. Yeah. Any questions? And yeah, thanks. Yeah.
The last time, like this time, like, if the Merkle tree was to wear pants, how would it vary? Like one big pant or lots of small pants?
Sorry, if it was what?
If the Merkle tree would wear pants, how would it vary? Like one big pant or like lots of small pants?
Yeah, that's a good question. I guess lots of small pants. Yeah.
So you're doing this to keep things off chain, right? It's cheaper. That's how you start.
Cheaper is the argument, yes.
So you still have to include. What do you include on chain? You're going to do a proof of the state roots on chain.
So the proof are basically this hashes. So this is the proof is an array of the hashes which are needed to produce the root hash.
Right. So what goes on chain?
So we inject the proof on chain, and what we store is the Merkle root itself. And yeah, we calculate then the proof, and if we end up at the Merkle root, this is the proof that it's valid, basically.
Can you update? Are you thinking of updating stuff? Or?
Yeah, you normally have an update function for the Merkle root if you want to. So if you're changing the Merkle tree, you have to update the root. This is a thing. So you also have some downtime in theory in between. But you could also, for example, have, if you don't want this, 2 Merkle roots and then just swap them out and maybe try both in computation to not have this downtime.
Last very quick question. You're thinking of this for one shard or for all the shards?
I'm not really aware how this sharding stuff works basically. So I think contract things have to stay on one shard, I heard before. Then one shard, I guess. Yeah.
But I think the proofs can be aggregated. You don't need to do it for different shards because it's only used for proof the existence, right? So
yes,
you can merge all of the states on different proofs. It's not a problem.
Mm.
You can use the same You can use the same root hash. I think that's
basically together with all shards, yeah, probably. All right, then, thank you.